Welcome, everybody. This is Breaking Bad, Abusing Belkin Home Automation Devices. Before we begin, I want to give a little intro to ourselves. My name is Scott. I'll be the software guy for the remainder of the presentation. I'm a security researcher. I've been in the business about 15 years. Currently, I'm a research director at Invincia Labs. Mostly what I focus on is new and novel offensive and defensive cyber capabilities.
I'm Joe Tannen. I'm the hardware guy. I'm a lead research engineer. I primarily work in mobile and embedded systems, so customizing and securing Android and other embedded Linux platforms.
So a little background about us and our company. Invincia Labs does a lot of work with embedded devices. We both create them, secure them, as Joe was talking about with mobile devices, and we also break them, my specialty. And we do this all for a lot of long-term R&D programs, looking at next generation kinds of embedded devices. So we thought, obviously we'd take our skill set and apply it to this new IoT realm and see what we could find. So what we're going to talk about today in particular is the security of the Wemo platform. And specifically, we're going to disclose two zero-day vulnerabilities, one of which allows us remote root access to any Wemo device. And the other one is effectively what you call a cross-site scripting vulnerability. It allows us to inject code into the Android Wemo app and run it in the context of the app. Along the way, we're also going to present two new techniques. One of them is a hardware authentication bypass technique that Joe's going to talk about, which we think is more generalizable than to just Wemo devices. That's why we're presenting it to you. And the other one is a way to leverage SQL injection vulnerabilities into SQL-like databases that we also think is more generalizable and other pen testers and vulnerability research might be able to use. So to start off, let's talk about what Wemo is. Wemo is Belkin's line of home automation devices that came out in 2012, about mid-2012. The idea was to be simple and easy to use, hooks up to equipment you already have. You don't need to buy a special hub or any other special gear, just the device. They started off with what you see in the top left corner there, which is the Wemo switch. Effectively allows you to turn any device that plugs into it on and off with your phone. They've since obviously expanded their line to roughly 20 different devices, to include everything from a Mr. Coffee pot, a crock pot, humidifier, room heater, etc. They all work roughly the same way, as I said before. You hook the device up to your home Wi-Fi, and then with the smartphone app, either locally on the same network, if you're on the same network, you use that local Wi-Fi network to communicate with the device, or if you're outside of that network, it uses the cloud to connect to that device. Of course, the device connects to the cloud through your Wi-Fi. Pretty standard for any IoT setup. And the reason we're interested in Wemo devices are threefold. One of them is because of this number from the end of 2015. It says they got 1.5 million devices deployed. It's a pretty good number. Another reason is that people seem to like them. I mean, other than that number, they've won a bunch of awards. Pretty usable, pretty user-friendly. People seem to like them. But the other reason is because you might remember seeing this headline from back in 2013, or this one in 2014. Both of which caused Belkin in 2015 to kind of put a stake in the sand and say, okay, we're going to look at the security of these devices, really going to patch things up, we're going to get better at this. Now, before we get into what we found with the devices today, I want to kind of talk about these prior headlines. So the first one from 2013 is by this independent researcher named Nitesh Tanjani. Effectively, what he found out is that he looked at a bunch of devices, but with the Belkin Wemo baby monitor, he found that there's an authentication token that's being sent in the clear over the internet. Anybody sniffing on from the local network out through the internet could grab that authentication token and reuse it to log into your baby monitor remotely. Not a good thing. The second headline you saw was from 2014, and that was an advisory released by IOActive, probably the thing you're most familiar with if you've heard about security of Wemo devices. And they found a whole bunch of stuff. Everything from hard-coded crypto keys you can use to sign your own firmware, all the way down to just command injection type stuff. Now, around the same time that last headline came out, there was a blog article by this guy named Brian Hart. And what he found was a very simple command injection vulnerability. If you've ever done anything with IoT or dealt with security of IoT, this is sort of the low-hanging fruit of IoT, right? Effectively, the element in this XML field here is being used as a parameter to a command that's being run with the system call, right? So it's just running a command and using the value of this XML entity as one of the parameters. Of course, if you just put backticks around that, as he's done here, it'll actually run that command before the command it's supposed to be running. And effectively, all this does is turn on Telnet and auto logs any connection into a root shell without authentication. Easy peasy. Standard low-hanging fruit for IoT. And that's still at the end of 2015. So much like the prior research, we have the same attack scenario. We presume that some malicious actor has gotten access to another machine on the same network as the Wemo device. Now, if this is your home PC, it's meant to be a home network, of course. We assume that's via phishing or drive-by download or something. They've compromised maybe your home PC and have gotten access to that. And then they can communicate directly with your Wemo device. And the way you communicate with the Wemo device is over universal plug and play. Here's what happens. You open up the app sends out a broadcast UPnP message, which is essentially just an HTTP message over UDP to a broadcast address. It says, hey, where are all the Wemo devices? Wemo devices respond with a unicast UDP message, essentially another HTTP message, and it says, here's the location of my device description file. Now, the device description file contains all the UPnP endpoints in it, essentially URLs that you send messages to communicate. For example, in the Wemo switch case, if you want to turn the switch on or off, you click that on-off button, you'll send a UPnP message, an HTTP message over TCP this time, to the UPnP controls basic event 1 UPnP endpoint, and the message itself will actually be the set binary state command. 1 or 0, on or off, right? Setting the binary state. Pretty easy stuff. Okay, so one of the other pieces of functionality that Wemo has that everybody seems to love is this idea of rules. You can create rules to do simple things like if you have all your lamps plugged into these Wemo switches and you go to bed at 10 o'clock every night, you don't want to forget to turn off the lights, you can set a rule that turns off those lights every night at 10 p.m. If you have your crock pot on medium for 5 hours, you want to set it to low to keep your dinner warm but not overcook it while you're at work, you can set a rule to do that too after, let's say, 5 hours go to low. Useful stuff. What we found is that, the way these things work is on the app, you have this interface that allows you to create these rules. When you hit the save button, it adds that rule to a SQLite database. If you don't know, SQLite is like a regular database just shrunk down into one file. When you're done editing the rules for a device, it takes that one file, sends it to the device, and the device uses a set of SQL queries stored in the firmware to unpack it, right, and update the rules in memory. What we found is that those rules are vulnerable to SQL injection. And here's how. This is the rule updating algorithm. We reverse engineered the firmware and kind of came up with, this is more to be seen as pseudocode than actual code. First thing it runs is load rules into memory. What that does is it queries the database, the rules table, for the type and the rule ID of all enabled rules, where state equals 1. Each one of those result rows, they take the rule ID from that and send it to the fetch target device ID function, the bottom function on this slide. That function uses the rule ID it got from the database to create yet another query and execute it. Now, I know you might be thinking, how is this insecure? Because you're using snprintf, and we all know that's a secure version of sprintf, right? So there's probably no issue here whatsoever. So let's go through a couple examples. In the benign case, right, a rule ID is supposed to be a number. It's the primary key of the database, so it's supposed to be a number. And we see at the top of the slide, you see that the rules table, initially, we have one rule in there, rule ID of 1. After the first query runs, we get one result back. We see the rule ID there as well, and I've bolded it so you can kind of trace it through here. And then the second query gets built as expected, right? We're going to select device ID where rule ID equals 1. Easy peasy. But the problem here is that SQLite does not enforce column type constraints, okay? So it doesn't have to be an integer. You can put that as anything to be anything you want. So let's say we did something like quote semicolon dash dash, a typical textbook SQL injection. Turns out if you trace this all the way down to the bottom, what you end up doing is making a query with an empty rule ID value. Semicolon is going to end that first SQL statement, and then dash dash is going to comment out everything else on that line. Again, textbook SQL injection. If you didn't know SQL injection before now, you do now. But that's great, right? Now we can put stack SQL queries together, right? We can put more things after that first semicolon, other statements. But what do we do with it now? And that's the same question we had. So we did what you would all do. We Googled it. Turns out the first result that Google throws back at us has an interesting thought. Some pen testers use SQL injection to SQLite databases to do the following. They use the attached database syntax. What that'll do is if there's another SQLite database on the same file system that you're on, you attach to it, and then you can query and pull data from that to use in your current set of queries or to put in your current database, the one you already have open. Turns out, though, if the SQLite database doesn't exist where you ask for it to, where you try to open it, it gets created there. Then you can create a database. So you can, in effect, store data that you have from the current database into this new one you've created. Well, let's say we created something with a .php extension in the web server's root directory. And then we added some text in there that looked suspiciously like PHP code. Well, the PHP interpreter is so simple that all it's going to do is search through that file looking for anything that looks like PHP code, and when it finds it, execute it, right? Now, this is an existing technique, as I said, we got from Googling around. Seems like a good idea. We'd love to use it. Problem is, we don't have PHP in the system. We're looking at this small little embedded device that doesn't exist. However, it did give us a really interesting idea. Well, we don't have the PHP command interpreter. We are working on a system that's based off of OpenWRT, right? All Windows devices are based on OpenWRT. OpenWRT uses the BusyBox suite of embedded Linux tools, right, to implement all of the basic Linux commands, to include binsh. And by default, binsh is the ash shell, not bash, but ash, which is a very, very simplified version of bash. In fact, so simple that really all it cares about when it's parsing input, what it really cares about is new lines and parentheses. Because a new line is what happens when you hit return, and parentheses essentially do subshells, right? Those backtick kind of things. But in ash, it's parentheses. So we said, okay, this is a command interpreter, a little bit more complicated than PHP. But is there a way that we can maybe create a SQLite file and then with purely SQL statements make it executable by an ash shell interpreter? Spoiler alert, the answer is yes. Here's how we do it. We care about that whole new line thing, right? So we have to figure out how to arbitrarily add new lines. What we have here is a simple create table statement. We're creating a table named Echo. It's got one column name is Echo. And you might be asking yourself, why did you put those things on separate lines? You can put that all in one line. And the reason is because SQLite, when you run that create statement, actually preserves that new line character. In other databases, they would actually get rid of it and say it's an extraneous character, we can save space. Not SQLite. By default, it preserves that new line character. What happens then when you run that file through BusyBox's ash shell is you get this first error here. It says SQLite not found. That's happening because it's interpreting the first word in that file to be a command name. And of course, there's no SQLite command in the system. But more importantly, it's interpreting everything after the word SQLite up until that new line as the parameters for that command that it cannot execute. Effectively, that means we've skipped a whole bunch of text we didn't want to deal with anyway, or a whole bunch of bytes we didn't want to deal with anyway in that file. That's good for us. Now all we got to do is deal with a second error that says unterminated quoted string. And we do that by adding another new line. So it turns out after a column definition in a create table statement, you can put these words without row ID. And I have no idea what they do. But I know they can be put after the column definitions, and they can be put on a new line. Which means that when we run this file again in BusyBox after doing that, we get that first SQLite error, but then we get this suspicious thing that says non-primary key. What's going on here is that the echo column name is being treated as the echo command because it's on its own line. There's a new line right before that parenthesis, the open paren, and there's a new line right after the closed paren. So the ash shell interpreter is actually interpreting that to be its own line. It's enclosed in parentheses, which means that it executes as a subcommand. Great, we have command execution. It's not arbitrary command execution because that column definition, I can only put so many things after the echo. I can put random things. So to get arbitrary command execution, we take a page back from the PHP example, right? We insert some data into that table we just created. And all we have to do is put a new line before and after the data we insert, and we can run whatever the heck we want. In this case, ls/. And you see at the bottom there, after a bunch of errors on other things that couldn't be executed, we get the output of our command. Cool, so now we have arbitrary command execution with hash. So this is what the malicious database actually looks like. Instead of, the malicious rules table of the database. So we put two rows in here. The first one is going to create a file in a particular location. I'm going to go over why that location is important in a moment. That's the first row. The second row actually inserts the command we want to execute, just like we just showed. Note that they both start with this double quote semicolon because they are actually injecting these statements. And then the command we want to run is the one we saw at the beginning that other guy used in the XML case, right? We just want to start up telnet to auto log us into a root shell. Okay, so now we've been able to create an executable SQLite database, right? But we still need to put it somewhere so it will execute. It is executable, but we need to get it to execute. So it's a two-step process. What we started doing is we started looking through the init scripts, right, for all the different services that start in the system. And in a networking init script, we found this, and this similar syntax is in some of the other init scripts, so this is the easiest one to work with. We saw this include /lib/network. We thought that's interesting. I wonder what that does. We went and found that in etc functions.sh. And if you look at here at this code, it's just a simple loop. All it's doing is it's treating the parameter that you pass it as a directory, reading all of the files with a .sh and sourcing them into the current file. That $$ file, that's sourcing. Sourcing just means read all the lines and execute them. That's really cool for us because it means we don't need execute permissions on the file we created. Because when we do attach database, it doesn't give it execute permissions. But this will read all of the data in that file and try and execute it. Exactly what we want. Okay, so now we know where to put the file to get it to execute, but now how do we actually execute it? Well, we essentially need the networking init scripts to run. We could always, unplug and plug the device back in, but that's not terribly helpful if we want a remote attack, right? So instead, what we found is that there is a particular UPnP endpoint called Wi-Fi setup 1. It's meant for when you initially pair the device with a Wi-Fi network. So when these devices come up, they create their own access point. You connect to that access point and then tell it what network to be on. The Wi-Fi setup endpoint is used for that purpose. When you are already paired, though, that endpoint is still active. We can still tell it to do things. In particular, we can say stop pair. That means I've given it a new Wi-Fi name. I want you to reboot all the networking stuff now, literally restart the networking subsystem so it uses that new access point. If we do that while it's already started, it just restarts the networking things and everything comes back up, right, as it was supposed to. So essentially, when we do that restarting of the network stuff, or the networking subsystem, we effectively run our script, which we're going to demo to you right now. Okay. So we have a device. We're going to just prove to you that it's up and running. Cool. And then we're going to prove to you that we don't currently have telnet running on the device. Okay, it didn't work. Now, we're going to run root.sh. Root.sh, as you can see, does a couple of curl calls and then effectively throws a few messages that are generated by some Python scripts. Okay, that's all it does. Okay. So I'm going to go over this in a second because we need to wait about a minute to a minute and a half for the networking subsystem to actually reboot. But what's happened right now is we've thrown the rules file over there, and then we kind of put it in sleep for 10 seconds just to give the firmware, it's a slow device, right? It's not a particularly powerful processor, the firmware a chance to unpack it. Okay, now we're sending the trigger. So what we're going to do is go back up and start pinging the device. And then I'm going to come back to the slides and explain to you what's going on. Okay, so this is the sort of anatomy of the attack. The first thing we need to do once we have this malicious rules file created is we need to set the device into a state to accept the rules. This actually took us a long time to figure out. It didn't work every time, we couldn't figure out why. You need to do a certain set of calls. That was those first two curl statements and then the first Python script to run. That sets the device in a state that when we then send it the malicious database, it'll actually properly unpack it and run our SQL injection. That SQL injection will write the file to the appropriate location. The next thing we need to do, which you saw in this as the trigger, is send it that stop pair message. And that's going to restart the networking subsystem. And the reason I'm showing you the slide right now is because, again, that takes about a minute to do. So hopefully by the time I'm done talking about this, we can go back and do the last step, which is tell that into the device. And let's see if that's working thus far. No, not yet. Waiting. Apologize about the dead air time. Also apologize about the voice. I got kind of a cold on the way over here. Worst thing to happen when you're doing a talk, right? Also, dead air time, worst thing that can happen during a talk, right? Oh, there we go. All right. So, oh, look at that. So we can type ID now and the network. And then show you the one on MIPS device here. And then lastly, we'll do cat the version of this device. And all right, and show you that we are actually on Belkin firmware right now, Belkin Wemo firmware. So there we go. That's how you would remotely root a Wemo device. Okay. Okay, so the takeaways from this. We obviously turned on Telnet D here, but we could have done anything else. We could have wget some malware and executed it, right? And that was a common question we've gotten from other people is what else? Okay, so you turn on Telnet, what's the big deal? Obviously, we demo that to you guys because that's what the security community wants to see. Think Mirai. We easily run Mirai on this. By default, Mirai compiles to MIPS. The other interesting part about this is that the only real remediation is a firmware update. So all these Wemo devices have a factory reset button on them. Hold it down, plug it in, wait 5 seconds, factory resets it. That doesn't remediate what we've done here at all. The only thing you can do is wait for the vendor to give you a firmware update, which of course is not ideal because you don't get to choose that. Also, the reason that's not ideal is that it is trivial to break their firmware update process. It's just a shell script. So we can easily break that and prevent you from ever updating your device, effectively meaning it's owned forever. This brings up sort of another issue though. What we did here is that while Belkin had this SQL injection vulnerability they coded, right? That's not the reason we got root. That's not the entire reason. There's this whole software, open source software stack that this stuff is built on, right? So SQLite provided us a way to do an arbitrary write as root because everything is running as root. Ash provided us a way to execute some commands. And then OpenWRT, the design of it itself, and it's designed so you can download it and modify it custom for your device, right? That provided us the actual trigger to execute, putting it in a certain direction and then restarting the stuff. So we need to start thinking about like the entire software stack that IoT is based on, not just the stuff that we write. I think it's an important takeaway from this whole exercise.
So while Scott was developing the remote exploit, he had very kind of coarse-grained feedback. Getting the LED blinking by doing something or putting a file in a very restricted location. We could see that that kind of stuff was happening, but we couldn't get deep into the guts of what all the processes were doing, what the individual process log files were, if we managed to crash anything, and other things like maybe even GDBing into a process. And these would all be things that we'd want to be able to do. So we looked at getting local root as well on the device so that we could get more fine-grained kind of introspection into what was going on. So what we ended up doing was just popping the thing apart, hunting around for ports, connecting to them, and seeing what we could get from there. Thankfully, the OpenWRT community wanted to get OpenWRT running on this device, like a vanilla version, and they'd already done some of the legwork to find out what the ports do, how to, what the connector pinouts were, things like that. So thanks to those guys. We cracked it open. We removed the application board. It's a high voltage relay. So this is the switch used to turn whatever's plugged into it on and off. We didn't want to have that high voltage stuff in there when we were poking around on it, so took that out. Unfortunately, the power supply for that, for the Wi-Fi board is on that application board. So we made a connector that plugs into a benchtop power supply, and that's what you see all the way on the left-hand side of the slide. Next to that is the console port, the debug UART, just TXRX. So we soldered onto that. Couldn't make a connector for it because those were just test pads. We ran all that over then to the breadboard you see on the far right and plugged in the USB to UART adapter as well as our benchtop power supply stuff. It kind of kept it from being too flimsy and just falling apart all the time. The serial console is just 57600 8N1. We'll use the Linux screen commands to connect up to it. Just got a regular familiar looking prompt. When we boot the device, we see the boot logs kind of scroll through, and then we get to a Linux console for logging in. First, we tried logging in with no password. That didn't work. Then we tried logging in, or no user rather. Then we tried logging in as root with no password. That also didn't work. And so they have guards on there that prevent you from just logging in. We thought, okay, well, what can we do now? Well, we have that firmware update that we picked apart and analyzed as part of our static analysis for the remote exploit development. And we had Etsy password, which contains all the users and their hashes for their credentials. So we pulled that hash out, we put it into our GPU farm, and 9 days later, someone else needed the GPU farm. So it resisted pretty well our attempts to crack into it. It's a reasonably strong password, So now what else can we do? We're kind of stuck at this login prompt. Well, if you look at all the boot messages, you can see that U-boot is booting up the Linux kernel, and it actually provides you with a mechanism for breaking into the U-boot console by spamming the 4 key while the device is booting. So we got onto the U-boot console using that. To modify the Linux startup process through U-boot, you can do a number of things. A lot of them can be set in different variables that are available on the system. You can print these variables using printenv, set them using setenv, and persist them across reboots with saveenv. And a lot of those kind of feed into the kernel boot process, things like where do you load it to, what are the arguments that you pass to the kernel. Unfortunately, when we tried modifying those, it actually modified the variables, but when we booted the kernel, the version of U-boot that Belkin compiled has static boot parameters depending on some other configuration values, so our modifications didn't stick. Well, U-boot runs in RAM, so is there any way that we could modify those static parameters? Turns out you can. They left in the functionality for arbitrarily peeking and poking RAM, so md.b and mm.b for peek and poke. And since U-boot runs in RAM, we were able to kind of dump the area in flash where we think U-boot lives. It's typically at the end, so it can load the kernel at the beginning and execute it nice and simply. And we found the boot parameters for the kernel that it was using. So we first tried to do things to init, some easy things, like put the system in recovery mode, single user mode, by using arguments like 1, capital S, single, something like that would get passed to init and say, hey, don't do your full boot sequence, just give us a root shell. That didn't work. So then we said, okay, well, if the normal init process isn't going to do what we want, why don't we just set init to binsh? That actually did work, kind of. It would run binsh, but the system looked like it was hung. And the reason for this is that there's no dev console node in the initial file system for when the kernel boots. There is no initrd or initramfs support built into this kernel. So what ends up happening is after boot, the normal init scripts create the dev node for the console. But since we didn't have that at this point in time, we tried non-interactively creating that by using -c and passing a command to binsh. We didn't get that working, and we didn't have enough feedback to kind of figure out what was going on, so we decided to kind of defer that and move on to a different mechanism. Modifying the Linux file system, like we saw, you can put a script in the init scripts that ends up starting up telnet. Is there anything else we can do? We don't necessarily want to run telnet in our case here because we might want to get on the system before the network is up. So look at doing something like removing that hash from that etc password file so that we don't need a password to log in. How do we access the flash? A lot of the times in U-boot, there are functionalities for manually reading and writing flash, and sometimes even to mount file systems from flash. None of those were in this version of U-boot, so we couldn't arbitrarily access flash in the stock U-boot. We could try clipping onto the flash, and the package on here is a small outline package, SOP, pretty easy to clip onto and access with an external writer. But some flashes, notably ones that are like stacked up on kind of smaller embedded systems, are difficult to get to. They're like BGA or sometimes like QFN, things like that. So we wanted to try to see if we could just purely with software and the console access we already had access the flash instead of physically clipping onto it. You can actually do this. You can use load B. That's another way to get stuff into the memory in U-boot from something external. In this case, we used Kermit to, ship something up with load B from the host. And then that boot M process that's used to boot the kernel uses those static arguments, but and it actually pulls the kernel from a fixed place as well. But Go will just execute whatever you tell it to execute as long as it's properly formatted for U-boot to be executed as an application like that. So we developed a custom application that can talk to the flash over SPI and then talk back to the user with UART and just use that to interactively modify the flash. So now that we can modify the flash, what do we add to it? And I mentioned a little bit about what we're going to add to it. We're going to modify etc password, but how is the file system structured? So how do we know where we're going to put this thing? There's two parts of the file system. There's a dynamic part, that's a JFFS2 partition, and there's a static part, it's a squashfs partition. The dynamic part can be read-write, the static part can only be read. And these are kind of blended together with an overlay file system, in this case Minifo. Newer versions of Wemo use overlayfs, but they still use similar semantics where they have a dynamic portion and a static portion. So what we did then was we read the SquashFS off the device. We validated that it's the same one from our firmware update image, just so we had some backtracking there. It was exactly the same. We pulled out the Etsy password, killed the hash, and then mounted up that JFFS2 block on our host development machine. You can't just use a regular block device for that because JFFS2 expects a memory technology device, an MTD, underneath of it. But there are ways to emulate that with Linux. And so you can look in our source code for how to do that. So we mounted that up, copied in the new Etsy password file, unmounted it, generated the patch, which was just a binary diff between the original JFFS2 chunk and the modified one. And then we shipped that patch up to the device and flashed it using our application. You can see that process here at the top. We load our program, we load the patch, we use the program to apply the patch, and just some informative stuff in there. We reboot the system, snip out all the kind of boot logs because those are kind of unnecessary, type root, and now we're in as root, no password required. So takeaways from this, in a lot of cases, people are trying to really lock down embedded systems. They want to make things like mobile phones and stuff very, very secure, so you can't poke around on them and muck about with them without having authorized firmware on them or decryption keys or whatever. On these cheaper embedded systems, that kind of stuff really isn't there. They don't validate that what they're booting is something that they're supposed to be booting. They don't check to see if you've changed anything in ways that they might not want you to change it. So kind of physical access in this case did equal root access, and that's probably the case on a lot of these cheaper embedded systems. Engineers don't like removing their test points and all from a PCB in production because that means that you have to make a new PCB and test it. So they'll kind of just leave those ports on there and just not populate them. So things like that are on these devices all the time. And that overlay thing that I did to add the Etsy password in, like I said, the overlay kind of mechanism is used in OpenWRT and all the other Belkin devices. So kind of anything that's derived from OpenWRT is likely to use that sort of dynamic static file system mechanism, and you should be able to modify it in a similar fashion.
Okay, so what we've now seen is we've seen two different ways to root a Wemo device, both remotely and locally, right? But we have to remember that the attack surface of any IoT device is more than that, right? It's not just the device. Oftentimes you see, especially online on blogs, people are like, oh, I got into this device. That's great and all, but there's more than that. There's the cloud that people have to connect to, and that's the whole idea of the IoT part, or the I part of IoT. In this case, Belkin expressly prohibits independent security researchers from testing their cloud infrastructure. Can kind of understand why, right? It's a shared resource, don't want to take that down. But the other thing that we do have in our possession that we can work with is a smartphone app. So Wemo's Android app in particular is built with a cross-platform mobile development framework called Cordova from the Apache Foundation. Effectively, the idea of this is that you can create your interface in HTML5 and CSS, and then obviously that can work on any mobile platform. And then they have this JavaScript bridge that allows that interface to talk to, or the other code, the native code, to talk to the interface. Native code in this case would be obviously Java on Android, and then it would be Objective-C or Swift on iOS devices. Also interesting with this is that if you just take the default project with Cordova and compile it up, you get these default permissions. You get access to the camera, the contacts, the location, the phone, and any sort of shared storage on the device, like an SD card. And in fact, in the Wemo case, they have these permissions as well. So we started looking at this. One of the interesting pieces of functionality that's provided by the app is the ability to change what they call the friendly name, the name that shows up on the device, on the app for all your devices. This makes a lot of sense. Say you buy 5 switches, right? And you want to plug different lamps into them in different parts of your home, living room, kitchen, bedroom. They all come with the name Wemo switch. You obviously want to change that to something more relevant, like kitchen lamp or bedroom lamp or whatever. So you use the UPnP endpoint control basic event 1, and you send a message that looks like this with the friendly name change to something like my switch. What that'll end up doing is actually rewriting that device description file. That's what you see in the bottom, and sending that back to the phone with the changed name, the modified name. Now, under the hood, here's what's happening. There, in one of the Java classes that Belkin wrote, you can see here these 2 lines of code. The first one just gets all the information that it knows about from the device, right, that it got from that device description file. It then uses that, calls a toString method on that to create this JavaScript string that it's then going to send to the interface, right? So it's actually, as you can see here, a very simple string concatenation to make that JavaScript string. In particular, we're interested in what happens in that toString function. And it turns out all that toString function does is concatenate together all the information it knows about the device in one giant string. To include, as you see on the right, the friendly name. End result is they'll have this JavaScript string that is sent to the interface that looks like this. And whatever we typed in as our name shows up there. The net effect on the device itself is the device actually parses this JSON file that gets created by all that stuff. And as you can see on the left there, the friendly name is highlighted, it's my switch, and then you see my switch in the app, right? So we had an interesting thought, like, well, what if that name wasn't quite as friendly, right? It was a lot less friendly. So we put in what you do normally when you're testing a web app, right? We put in some default cross-site scripting type stuff. In particular, we did the alert pwned message, sent that to the device, and much to our surprise, it echoed the same thing back to us in the device description file. The difference here is it's HTML escaped, right? Which is fine. The app will auto unescape that stuff. But interestingly, there was no sanitization that took place. Now, if you try to do the same thing on the app, if you tried to, because obviously there's an interface to change the friendly name on the app, it'll give you two errors. One, it'll tell you that it can only be 30 characters long, and two, it'll tell you that most of the characters that I've typed in here are invalid. You do not get that error when you do this by sending a message directly to the device. It's probably also important to note here, at this point, I didn't mention it earlier when we were talking about UPnP, all the communication with WeMo devices are unencrypted and unauthenticated when you're on that local network, right? And that's something that actually we've seen some news articles that kind of get that one wrong. So it's very easy for us to just send this message. Now, what happens, fun enough, is we get our standard alert box that pops up and says, oh, okay, that ran. If you look on the left here, I've kind of dissected the string that we put in, the malicious string, and it's very much similar to the SQL injection case, right? We close that friendly name field, then we close the entire JSON message, then we close the current JavaScript statement, run a set of stack statements, one of them being our alert box, the other one being the console log message. The reason we use the console.log, it's like the dash in the SQLite case. It effectively comments everything else out. It turns out if you put the / in there, stuff breaks. So we had to come up with another way, and that's just what we came up with. Oh, the other thing to note is we ended the friendly name. We didn't put a name in there because we wanted to actually see the effect. If the alert box didn't pop up, we still want to know the injection took place. If you had put a name in there and not put something that popped up on the screen, the user would not know that anything changed, right? They would just still see the friendly name and the code would run in the background. There'd be no visible cue that we had done anything. Which brings us to our second demo. Okay, we recorded this one because there's a couple of things going on. On the left, you see we have the phone up, the app up. On the top screen on the right there, you're going to see how our actual attack on this. And I've enumerated the command here so you can see it's very simple. We're just running a script and piping it to netcat to get on the device, okay? What you see there is the result that echoes back what we put in. You can see we put in a whole bunch of JavaScript this time. Particularly, you can see a URL callback. Now, when we refresh the device, you'll see it pull down. What our JavaScript did that we inject is actually, we just asked it to pull down another file, pwn, right? Which is a giant JavaScript file that contains two pieces of functionality. You saw it happen there. So the initial inject just pulled down that file. What that file does is two things. The first thing it does is it reads all of the pictures from your camera, any picture you've taken with your camera, and it downloads them to us. You just saw that show up in the bottom half of the screen there. And then we're gonna show you now that in fact is a picture that downloaded. And it's a wonderful picture of our hardware guy. He didn't know I was gonna take that picture, by the way. So then, as you see, when that was going on, you see the second piece of functionality happened. If you look in the top screen there, it's actually beaconing back your location. There we go, it shows up in the bottom there as well. So it's actually taking your GPS location and sending it back to us. More interestingly, as you see in a moment, when we hit the home button on the Ender device in the left pane, and we put the app into the background, we continue to get your location beacon to us, right? So if you had switched to another app, it'd be the same thing. The app still goes in the background. So you turn off your lights, you hit the home button, you put it in your pocket, you go to the store, because your phone still connects to the internet, I still get the location where you are. I've just turned your phone into a GPS tracker because your IoT's app was kind of insecure. Okay, so takeaways from that. First and foremost, this has nothing to do with the previous two exploits, right? We did not need to root the device for this. We used the device's normal functionality, set the friendly name, to set it to something malicious, okay? You don't have to have root access to the device. I think it's really important to stress. The second thing is we want to talk about the second and third order effects of IoT. That's what we're starting to call this stuff. So first order effect is I break into someone's device, what do we focus on? And I put a botnet there and it DDoSes Brian Krebs' website. Oh boy, that's terrible. But these are the second and third order effects, right? Why is it the case that if I can do something to your device, I can turn your phone into a GPS tracker, right? Why is it the case that an IoT device like a crock pot could make this stuff less secure, right? Well, I can think of this particularly interesting case where imagine I was some bad guy and I had done this to your device and I started downloading all the pictures and I found that there were some pictures of you maybe cheating on your spouse. And I was bad guy, oh, this is great blackmail stuff. And I go back and I blackmail you and you got to pay me all this money. It's this ridiculous scenario, right? All because you wanted to have a crock pot that could connect to the internet, right? It seems a little ridiculous, right? That we now have to kind of put on the same scale, weigh the security of your phone with having an internet connected crock pot. That doesn't seem like it should be on the same scale. We also think that as time goes on and this stuff gets more prolific, you're going to see more and more of these second and third order effects. This is just one, and it's the first instance that we know of that anyone's used an IoT device to kind of hack into your phone and run arbitrary code. Okay, so disclosure timeline, like any good security researcher, we disclose these things to Belkin. Initial disclosure happened on August 11th. They verified them same day. I think this is important. I want to stress that one of the reasons we did this is we also want to make their products better, right? We want to have a good relationship with vendors as good security professionals. We should be doing that. So the same day, within an hour, they actually got back to us and verified that all of our vulnerabilities work on newer versions of software than we had. That's great. A couple weeks later, they actually came out with the fix to the app and on the Play Store and gave us a nice little credit there. And then they finally figured out how they want to fix the SQL injection vulnerability a few weeks later. And then just this week, they finally released the firmware update. So go and update your firmware. So lastly, you want to note that all of the code for how we did all this stuff, we're going to release online. It's not up now, but it will be. Also on our blog at invincialabs.com, we're going to take each of the three things we talked about today, and we will have blog articles up there for them. For the SQLite as a shell script stuff, that's also going to be a separate blog because, again, we hope that's something that the community can reuse. And if you have an IoT device or thinking of creating one and you haven't talked to us or somebody like us, we think that's probably a good idea that you do that because nobody wants their device on this slide. And with that, thank you for coming, and we'll take any questions you might have. No? No one? Please.
You said Belkin is well ahead of the curve when it comes to giving devices. I mean, obviously, you selected them, you had a whole range of options. How bad is it? How good is it?
For Belkin, so the question was, how bad is it or how good is it for Belkin in particular, I assume you're asking?
Just the landscape in general.
Oh, so I think, yeah, Belkin is probably better than a lot of folks. I mean, as you saw from the headlines at the beginning, they've had some issues in the past and they've done a lot to try and fix those. A lot of that low-hanging fruit stuff, like those command injections with XML elements, weren't there. We actually had to work with this one. You saw this is a multi-step process. Even though there was a SQL injection, it took a lot more to get it to run. As Joe told you, they actually did a pretty good job on the hardware side of things. There was a password that wasn't easily cracked. They'd taken a whole bunch of functionality out of the bootloader. Yeah, they left some test points on and whatnot. But generally, I think that's probably better than the average case IoT product. And again, that's one of the reasons we did this is that we didn't want to just say, hey, look, we found something on a trip and bought it at the airport, and turns out that we can break into this thing. It seems kind of obvious, right? We want to take somebody that really cares about this stuff as a name brand in consumer electronics.
And we did find at least another device where on the user accessible GUI thing on a screen, you could type something in and it would do one of those backtick type command executions and root the device. So there are that kind of low-hanging fruit still in other production devices.
Yeah. Any other questions?
Well, one question about your attack, the first one was based on the standard open source like Linux-based operating system. So what about IoT devices that do not use Linux-based systems, some other? So do you have any examples from that or anything?
So the question was, what about IoT devices that don't use Linux-based systems? Most of the ones we've looked at do use Linux-based systems. In fact, most of the ones that I've even seen at other conference presentations do use Linux-based systems. So I can't actually talk about experience we've had with non-Linux-based ones. Yes?
I noticed that they posted a firmware update that's part of the reaction to this, but it sounds like they don't check signatures on those firmware updates. So would your attack against their firmware still likely work, or another version of it?
So the hardware attack, you mean?
Yeah.
Yeah. Okay, so the question was, sorry, let me repeat it. They don't seem to be checking their firmware updates, so would the signatures on them, so would our firmware attack still work? One thing I'll note is there in the firmware update process, we looked into it, they actually are doing signature checks when they download stuff. It's not encrypted, but it is signed, so they will do that check and not update if you don't have the correct signature. But I'll let Joe talk about whether it should still work on the hardware side of things.
The hardware stuff utilizes the bootloader, and their update process doesn't appear to modify the bootloader at all. So we should be able to still get our local root in newer versions of firmware unless they modify the bootloader. Their normal firmware update's kind of an A/B process, make it safe. You're running in B, and then they change A, and then the bootloader validates that A got done correctly, and then it switches to A. But there's no alternate place to put the bootloader. So if they were to if you were to unplug it in the middle, you'd brick your device. So they're probably going to be less likely to modify the bootloader ever in an update.
The hardware attack, but you only manage to hack your own device and not gathering any information to attack other devices.
So the question is, with the hardware attack, we only rooted our own device and not any ones remotely on the cloud. That's correct, and that was the intent. We wanted to get more introspection into our device so that we could make a better remote exploit, make it more reliable, or even, Scott actually figured it out before I got the local root, but if he hadn't, then we could have used that to try to help us see what we were doing wrong.
Yeah, I mean, so I think in that case, the hardware thing just became one of those issues where, well, wait, we have the device physically. Obviously, we can get a root shell on the device because we have it. And it became a little difficult when we were trying a bunch of things. We said, okay, now we're going to make this happen, right? Any other questions?
How long did the first attack with the SQL injection take to figure out and analyze? And,
Yeah. So it took, I'll be honest, it took actually, I mean, of course, we weren't doing this full time, right? Sort of nights and weekends kind of work. But it probably took us a good 2 months. And the reason is because, as I said, the SQL injection itself doesn't give you a whole lot, right? So someone asked me before, how long did it take me to figure out the whole SQLite as a shell script thing? And that was actually 2 hours. It wasn't actually that hard once you figured out what the Ash shell is going to do. But getting to the point where you're like, what else can I use besides PHP, right, to try and do the same type of thing? I mean, that was just an idea that we had. Maybe we could do that. It took a while. So it did take quite a bit of time to figure out how to gain execution just from that simple vulnerability. Also, we looked at some other things we thought might be vulnerable in that time.
Okay, so we're going to ask for just one more question because we're about to run out of time. Unless there are no more questions.
All right, well, thank you very much.